Hello students, welcome to mathematics class. So in the last class we have discussed Lorentz and Taylor's theorem. So now let us discuss the examples on those two theorems. So here the given example is expand the series of the function f of z equal to 1 divided by z square minus 3z plus 2 in the regions. The first region is mod z greater than 0 and less than 1, and mod z greater than 1 less than 2, and mod z greater than 2. So in these three regions we need to expand the given function f of z equal to 1 divided by z square minus 3z plus 2. To expand the Lorentz and Taylor series, the function must be a linear function in z. So but here it is a quadratic equation, so therefore we need to reduce that quadratic equation to the linear form, because we are going to expand those two series with respect to the binomial expansions 1 minus x whole power minus 1 and 1 plus x whole power minus 1. So means the function in the that z must be of the form 1 plus z or 1 minus z. So but here it is a quadratic equation, then we need to find the factors of this equation, and finally we need to write those two factors in the form of 1 plus x or 1 minus x, and here in these two mod x is less than 1. So this is the condition for the expansion of these two series 1 minus x whole power minus 1 and 1 plus x whole power minus 1. So here the value of mod x must be less than 1. So otherwise we cannot expand those two series. So here 1 minus x whole power minus 1 equal to 1 plus x square plus x cube and so on. So this is an infinite series, and similarly 1 plus x whole power minus 1. So that is equal to 1 minus x plus x square minus x cube and so on up to infinity. So therefore whatever the function given, so that function must be reduced to 1 plus z or 1 minus z. So accordingly we need to adjust the terms by taking common either the constant or the z. So here we have one condition: if mod z is less than any constant, if mod z is less than any constant, then take the constant common from the factor, and if mod z is greater than any constant, then take the z common from that factor. So this condition is very important. Whenever mod z is less than some constant, take the constant outside from the factor. If mod z is greater than k, then take the z out from the factor. So this is the important condition to reduce the factor in the form of 1 plus z or 1 minus z. So now let us consider the function. Now consider z square minus 3z plus 2. So here this can be written as z minus 1 into z minus 2. So these two are the factors of that quadratic equation. So therefore f of z is equal to 1 divided by z square minus 3z plus 2, which is equal to 1 by z minus 1 z minus 2. Then now f of z equal to 1 divided by z minus 1 z minus 2. So for the expansion of the function, the denominator of the given function should contain only one factor. So but here it is a product of two factors, then separate this as a divided by z minus 1 plus b divided by z minus 2 by using the partial fraction. So after solving the partial fraction, we get a equal to minus 1 and b equal to plus 1. Therefore f of z becomes minus 1 divided by z minus 1 plus 1 divided by z minus 2, or which is equal to 1 divided by z minus 2 plus 1 divided by z minus 1. So now this is the reduced f of z. So means whatever may be the given function, we need to reduce that function to the form of 1 divided by z plus a or 1 divided by z minus a. Means there should be only one linear factor in the denominator of the given function. Then we can expand the Taylor's or Lorentz series. And next here, now this is f of z 1 by z minus 2 plus 1 by z minus 1. Then let us expand this function according to the given regions. The first region given is 0 less than mod z less than 1. So here we know that mod z is less than 1. So according to the condition, whenever mod z less than 1, then take the constant outside from the given linear factor. So now given f of z equal to 1 divided by z minus 2 plus 1 divided by z minus 1. So here and always that should be of the form 1 plus z or 1 minus z. So like that we need to adjust the factors in the denominator. So it is equal to, now since mod z is less than 1, then we can say that mod z by 2 is also less than 1 here, because in the expansions, that 1 plus x whole power minus 1 and 1 minus x whole power minus 1, mod x is less than 1, then only we can apply these two expansions. So therefore here, to expand these two, we need to reduce the term which is less than 1, either it may be or by taking a constant outside or by taking the z outside. So whenever mod z is less than some constant, take the constant outside, and if mod z is greater, take that z outside from the given factor. So here we know that z by 2 is less than 1, and here we have 2. So therefore we can take that 2 common. So here we are taking that minus 2, because we need to reduce that to 1 plus z or 1 minus z. So then that is 1 minus z by 2 plus, here take minus 1 common, then that is 1 minus z. So therefore minus 1 by 2 outside, and take this to the numerator, that is 1 minus z by 2 whole power minus 1 minus 1 minus z whole power minus 1. So here we have taken minus 2 common from the first factor, because mod z is less than some constant, then take the constant which is present in the linear factor. So that's why we are taking that minus 2 outside, and here 1 is there, we have taken minus 1 outside. Then it is equal to minus 1 by 2, and expansion of this one, it is similar to 1 minus x whole power minus 1, that is 1 plus z by 2 plus z square by 4 plus z cube by 8 and so on, minus 1 plus z square plus z cube and so on up to infinity. So since both are the so here this is minus 1, right, again f of z, this is minus 1 and this is plus. So therefore this becomes minus 1 and here it is minus 1, then minus and minus will get cancelled, this becomes plus. That is the only correction here. This is minus 1, So minus and minus will get cancelled, so that becomes plus. And now here this is minus 1 by 2 and this is plus. Now minus 1 by 2, and we can write this expansion as in the form of the series, that is minus 1 by 2 summation over n equal to 0 to infinity z by 2 whole power n plus summation over n equal to 0 to infinity z power n. So therefore this is the expansion of the function in the first region. So in the first region the series is Taylor's series, because whenever the expansion contain only positive powers of z, so that series is Taylor's series. If the expansion contain both positive and negative powers of z, then it is called Lorentz series. The next region is 1 less than mod z less than 2. Now split this inequality as 1 less than mod z, and this implies that 1 by mod z less than 1. So we should always reduce the term which is less than 1, that is very important. And second inequality is mod z less than 2, then it implies that mod z by 2 is less than 1. So here 1 by z and z by 2, so these two are less than 1. So therefore in the given function we need to adjust the terms accordingly, 1 by z and z by 2. Now the given function f of z is equal to 1 by z minus 2 plus minus 1 divided by z minus 1, right, or this is equal to 1 by z minus 2 minus 1 by z minus 1. Now in the first factor we have z minus 2. So we know that whenever mod z is less than some constant, then take that constant outside the factor. So here mod z greater than 2, then we need to take that minus 2 outside the factor, and here z minus 1. So here we know that mod z is greater than 1 or 1 less than mod z. Whenever z is greater, we need to take that z outside. So let us follow the same thing. Here minus 2 common, then it is 1 minus z by 2 minus, as it is. Here we need to take that z outside, then 1 minus 1 by z. So according to this inequality, we know that 1 by z less than 1, here we got 1 by z, and z by 2 less than 1, so here we have z by 2. So now we can expand these two by using the identities 1 plus x whole power minus 1 and 1 minus x whole power minus 1. So until we get the value of x less than 1, we cannot expand the series directly. So that's why to make that quantity less than 1, we are taking that constants and z outside accordingly. So therefore now here this is equal to, here minus 1 by 2 as it is, then take this to the numerator, 1 minus z by 2 whole power minus 1 and minus, here 1 by z as it is, and take this 1 minus 1 by z to numerator. So now this becomes minus 1 by 2 into 1 minus z by 2 whole power minus 1 and 1 by z minus 1 by z whole power minus 1. Then write the expansion of this one. This is minus 2, and here 1 minus x whole power minus 1, where x less than 1. So therefore 1 plus z by 2 plus z square by 4, and so on up to infinity, minus 1 by z. Here this is 1 plus 1 by z plus 1 by z square plus 1 by z cube, and so on up to infinity. So now write this in the summation form. Summation over n equal to 0 to infinity z by 2 whole power n minus 1 by z summation over n equal to 0 to infinity 1 by z whole power n. So here this series is having both positive and negative powers of z. Here we have 1 by z means z power minus 1, 1 by z square z power minus 2, 1 by z cube z power minus 3, and so on. So therefore this is the Lorentz series. If the expansion is having both negative and positive powers of z, so that expansion will become the Lorentz expansion. If it is having only positive powers of z, then that is nothing but Taylor's expansion. The next region is mod z greater than 2, or this inequality can be written as 2 less than mod z. So to reduce this one as less than 1, so that will become 2 by z less than 1. So by dividing z on both sides, or simply taking this z to LHS. So therefore 2 by z less than 1. Then we need to adjust these two denominators such that the quantity must be less than 1. Whenever z is greater, then we need to take z common. So therefore it is equal to 1 divided by, here z common, remaining 1 minus 2 by z minus. Here also same thing, because only one inequality is given, no problem. Here also z common, 1 minus 1 by z. Then this is equal to 1 by z into 1 minus 2 by z whole power minus 1 minus 1 by z, 1 minus 1 by z whole power minus 1. So it is 1 by z. We can write this directly as the summation form, that is sigma summation over n equal to 0 to infinity. So here whatever the term is there, consider the same, that is 2 by z whole power n minus 1 by z, here also same, n summation over n equal to 0 to infinity. In place of x, whatever we have, that keep as it is and whole power n. So it is the expansion of the function in the region mod z greater than 2. So therefore here, depending on the given region, the same function can be expanded as Taylor series or Lorentz series. Now this is the Lorentz series. Whenever z is in denominator in the expansion, so then that series will be considered as Lorentz series, and whenever z is only in numerator, so that series is nothing but Taylor's series. So therefore this is the expansion of the given function in the respective regions. The next example, expand f of z equal to 1 divided by z minus 1 into z minus 3 over the regions 0 less than mod z less than 1, 1 less than mod z less than 3, mod z greater than 3. So it is also similar to the previous example only. So first let us factorize the given function such that there should be only one linear factor in the denominator. So therefore now applying the partial fraction, that f of z equal to 1 divided by z minus 1 into z minus 3, and that can be written as a by z minus 1 plus b by z minus 3. So by applying the partial fraction, we got a equal to minus 1 by 2 and b equal to plus 1 by 2. So therefore f of z equal to, in place of a, minus 1 by 2, and in place of b, 1 by 2. We can take that 1 by 2 common, so 1 by 2 outside, then remaining plus 1 divided by z minus 3, and here it is minus 1 divided by z minus 1. So now it is simplified f of z, and now we need to consider this one only for the expansion. Now the first region, 0 less than mod z less than 1. 0 less than mod z means that mod z is always positive, that is the meaning, and mod z less than 1. So whenever mod z is less than some constant, then take the constant which is present in the linear factor, that is the condition. So therefore now consider f of z equal to 1 by 2, 1 divided by z minus 3 minus 1 divided by z minus 1. So here 1 by 2 as it is. Now which term we need to take common? So here z is less than constant means we need to take that constant outside. So here the constant term is minus 3, so that becomes 1 minus z by 3 minus, here the constant thing is minus 1, so minus 1, 1 minus z. So it is the simple trick to find the common term. Now it is equal to 1 by 2, here minus 1 by 3 as it is. Now take the remaining term to the numerator, so that becomes 1 minus z by 3 whole power minus 1, and here minus into minus become plus, and 1 minus z whole power minus 1. Now you can expand this, or you can directly write the summation form. So it is equal to 1 by 2, here minus 1 by 3 as it is, summation over n equal to 0 to infinity. In place of x we have z by 3 whole power n plus, here summation over n equal to 0 to infinity z whole power n. So this is the expansion of the given series, and here there is no z in the denominator, so therefore it is Taylor's series. The next region, 1 less than mod z less than 3. Now split this inequality, 1 less than mod z and mod z less than 3. Whenever 3 is present, then take that 3 outside, because mod z is less than the constant, and in the factor if 1 is present, then take the z outside, because 1 is less than mod z means we need to take z from that factor where 1 is present, and mod z is less than 3, and here we need to take the 3 outside, because mod z less than 3. If mod z is less than constant, take the constant outside. If constant is less than z, then take the z outside. Means in this inequality, whichever is greater, that greater quantity must be taken outside. So 1 by 2, here 3 is greater, so therefore here we have 3 and with negative sign, so therefore it is minus 3, 1 minus z by 3 minus 1 divided by, here z minus 1, so 1 is present and z is greater in this inequality, so therefore z into 1 minus 1 by z. This is the way to take the common term from the factor. Then 1 by 2, here 1 by 3 as it is, 1 minus z by 3 whole power minus 1 minus 1 by z into 1 minus 1 by z whole power minus 1. Then it is equal to 1 by 2 minus 1 by 3 into summation over n equal to 0 to infinity z by 3 whole power n minus 1 by z into summation over n equal to 0 to infinity 1 by z whole power n. So it is Lorentz series, because in the second expansion we have z in the denominator. If z is present in the denominator, then that is the Lorentz series. Then the next region is mod z greater than 3. So here only one inequality is given, and mod z greater than 3. It implies that z should be taken outside, because it implies that 3 less than mod z, whichever is greater, that greater thing should be take outside. So therefore here f of z equal to 1 by 2 1 by z minus 3 minus 1 by z minus 1, it is equal to 1 by 2. Here z is greater, and here irrespective of the constant values we need to take that z outside. So 1 divided by z into 1 minus 3 by z minus 1 by z into 1 minus 1 by z. This is equal to 1 by 2. Here 1 by z into 1 minus 3 by z whole power minus 1 minus 1 by z into 1 minus 1 by z whole power minus 1. This is equal to 1 by 2 1 by z. Then write this in the summation form, that is summation over n equal to 0 to infinity 3 by z whole power n minus 1 by z summation over n equal to 0 to infinity 1 by z whole power n. So therefore this is the required expansion of the given function.